With this concept, we can start to talk about metals, insulators, and semiconductors. In a metal, the atoms usually have fewer than 4 electrons in the outermost orbit. The metal's outermost electrons are not sufficient to fill all the spaces in the shaded band. As a result, the valence band is only partially filled. The electrons in the partially filled band can freely move around to conduct electricity. In an insulator, there is a completely full valence band and a completely empty conduction band. As a result, there is no electron to move around and no electrical conduction in the insulating material. It is possible that some energy is applied to the system, that some electrons in the valence band are excited to the conduction band. In that case, the electrons in the conduction band as well as holes in the valence band can move around to conduct electricity. Semiconductors have similar band diagrams to those of insulators, except that semiconductors usually have smaller band gaps. As a result, energy supplied at room temperature is sufficient to excite a considerable amount of electrons from the valence band to the conduction band of a semiconductor that allows some electrical conduction. A material with a full valence band and empty conduction band can be insulator or semiconductor depending on the size of its band gap and the temperature of the operation environment. From this, probably, you can think of a simple application of semiconductor material to be used as an electrical thermometer because its resistivity changes with temperature. However, it is not an attractive option when compared with other devices we are going to describe later.